Good morning. Today we'll discuss about Friedel-Crafts reaction. There are two types. One is the Friedel-Crafts alkylation reaction and the second one is Friedel-Crafts acylation reaction. So the first one, Friedel-Crafts alkylation. So here, when the benzene reacts with alkyl halides in presence of anhydrous aluminum chloride, it forms an alkyl benzene and along with hydrogen halide. Okay, so here the aim is introducing alkyl group into the benzene ring. So here the main aim is introducing say alkyl group into the benzene ring, and the reactivity of alkyl halide decreases as you move from chloride to iodide. So alkyl chloride is more reactive than alkyl bromide or in terms of alkyl iodide. Okay, we've taken one example when the benzene is made to react with methyl chloride in presence of anhydrous aluminum chloride, it gives methyl benzene, or trade name is toluene and HCl. Okay, so the introducing CH3 group, which is an electron donating group, it increases the electron density on benzene ring and it favors once again towards the electrophilic reaction. So thereby one can add the one more methyl group into the ring. Say when the methyl benzene is made to react with one more molecule of methyl chloride, it gives say dimethyl benzene, or it is said to be a orthoxylene, and along with which the para product is also formed, that is paraxylene are also obtained. Okay, so now here anhydrous aluminum chloride is used as a catalyst. It is a Lewis acid, and similarly other Lewis acids can also be used as a catalyst, say like BF3 or FeCl3 or SnCl4 or H3PO4, etc. Okay, so the mechanism of the reaction can be explained like this. So once again, the mechanism of the reaction can be explained by three steps. That means there are three steps. One is the generation of electrophile, and the second one is attack of the electrophile on benzene ring and formation of carbocation, or it is also known as uranium ion. Okay, say the third step is the loss of proton. The third step is loss of proton, so it retains the aromaticity. Okay, in the first step, generation of electrophile, so that is electrophile, here alkyl carbocation is formed when methyl chloride reacts with AlCl3 it gives intermediate compound and which decomposes to give say methyl carbocation and aluminium chloride, that is AlCl4 anion. Okay, so this formed electrophile, that is CH3 plus, it attacks the benzene ring. In the second step, methyl group attacks the benzene ring, and which is a slow step, and forms say the compound which has lost the aromaticity. That means say due to the attack of this carbocation or say carbonium ion on benzene ring, say these pi electrons are shifted, and thereby the electrophile, that is CH3, is attached to the ring, and thereby this site got positive charge. Now this positive charge drags the electrons, pulls the electrons from this pi bond, and once again there is a shifting of electron. So okay, from one bond to, that means one pi bond to another place. So thereby there is a shifting of positive charge. So as it is shown here. So and this is the hybrid structure of resonance, and when the ion exhibits the resonance, means it is a stable one, or it is said to be a resonance stabilized say ion. Okay, and which has lost the aromaticity because the pi electrons are not say uniformly distributed, they are delocalized, or they are say concentrated particular portion, hence it is said to be it has lost aromaticity. The third one, loss of proton to retain the aromaticity. That means the H plus ion, this H plus is lost and it is given back to the, say, AlCl4 minus, and thereby the ring attains or achieves once again the aromaticity by losing that proton, and that will be taken up by this counter ion, that is AlCl4 minus, which gives HCl and AlCl3. Once again the catalyst is regenerated. Here the catalyst is regenerated. Okay. So now in the similar way, see, the reaction of ethyl chloride can be conducted where this benzene will be substituted by ethyl group C2H5. Similarly CH3CH2 CH, say this is a N-propyl bromide, and this is used, so it gives not a N-propyl benzene, it gives isopropyl benzene, because when the in the first step when it reacts with the catalyst, that is aluminum chloride, this itself undergoes structural rearrangement or a skeletal rearrangement, and it forms a carbocation, and that is in the form of isopropyl cation. It's a isopropyl cation, and that will attack the benzene ring to give this product. This is the isopropyl benzene. This one is isopropyl benzene. Okay. So the next one, we can take one more example. Say the next example is when the benzene is made to react with N-propyl chloride, it gives, say, isopropyl benzene but not N-propyl benzene. So during the reaction with, say, catalyst, it undergoes skeletal rearrangement or molecular rearrangement to give the isopropyl carbocation, and that reacts or acts as a electrophile, and that attacks the benzene, and it gives the product isopropyl benzene but not N-propyl benzene. Okay. Similarly, say one can explain the alkylation reaction with alkenes. So even alkenes or alcohols, they react with the benzene to give, say, alkyl substituted compounds. For example, when the alkene, okay, say 1,2-butene is taken, it gives tertiary butyl benzene. Okay. Similarly, Prandtl-Kraft reaction with ethyl chloride or, say, N-propyl bromide, the reactions are like this, and they give the respective products. Okay. So with this we will discuss in the next class, say, that is with Prandtl-Kraft's acylation reactions. Thank you.